around that. What is your talk about?
RBAC and users and registry
RBAC and end users and how to authenticate users with either tokens or certificates. My talk is on injecting TLS certificates into every pod of your cluster so that they can natively speak TLS across the network. Pardon me?
Do you know what the discount is and how we get it?
It is for everybody who's registering now. So, to get to it, cncf.io is the website, the Cloud Native Computing Foundation. If you scroll down several pages, all of their conferences are listed. Click that slider till you find the Cloud Native, and it'll be listed there that you can now register for a discount. It's 350 less than what it was. They also, if you've been laid off, they'll also sponsor your ticket. So, yeah.
Thank you. For our last speaker tonight, a man known as Ahmet. Welcome.
All right, hello everyone. Thanks for coming out. I appreciate the sponsors for putting this together as well. So we'll be talking today about a little bit about controllers actually, and I want to kind of take you to a journey into how to productionize the controllers that you might be deploying into your clusters. My name is Ahmet Balkan. I am actually unemployed. You might have an idea of what my prior affiliations were. So today we'll talk about controllers. So if you really think about what a controller is, it is basically a loop, right? It gets the desired state of the world and it actuates that state either on Kubernetes or elsewhere. You might have heard this example about you can create an object in Kubernetes that goes and orders a pizza from Domino's, right? So that is well within the capabilities of Kubernetes, depending on the controller that you might be writing. So essentially, a controller watches the Kubernetes API for changes on a particular resource type and goes and does something. It might be within Kubernetes or an external API. So now I'm actually going to ask, you probably heard about Kube Controller Manager, which is basically this process that contains some 30 controllers within itself, I think. For example, you create a service account, it has a secret or a token for that service account. It goes and cleans up your old jobs. It does, it manages the deployment control. It manages the stateful set control, right? So it does a lot of stuff. We actually hear things Kube Scheduler, which is responsible for assigning pods to nodes. Is that a controller, do you think? Yeah, Tiffany says yes, yep. How about Kubelet? Do you think Kubelet is a controller? Some people say yes, nobody's sure though, right? So Kubelet is actually a controller. It goes and watches the pods that is assigned to itself and invokes the container runtime interface to create that pod on Docker containerd, right? So that is a controller. It does something, watches Kubernetes API, creates something as a result. Who thinks Kube API server itself is a controller? One person back there. Do you know why? No idea. Okay. So Kube API server actually is a controller too. It watches all the resources for the purposes of garbage collection. When you delete an object, if a parent object is deleted, for example, if you delete a deployment, all its pods and replica sets, whatnot get deleted. How do you think that happens? So API server maintains a graph of all the resources in the Kubernetes to be able to calculate that graph to go perform that garbage collection. So all these things are controllers, and you're using a lot of controllers more, right? You're using Cert Manager, name something, I don't know, like Ingress controllers, right? There's so many stuff out there that you're using, but is it actually production ready? Does it scale? That's a good question. You might sooner than later find out if you actually start to run at a large scale. So this is going to be the topic of this talk. So you might actually wonder about how does a controller do that? The answer is the informer machinery. There's a lot of there are a lot of blog posts out there if you want to go learn about this topic particularly. But the bottom of it is Kubernetes does a list and then a watch. If something changes, it notifies your controller, right? So the informer machinery itself comes from the open source. It does contain a little cache to prevent extra GET requests. So if an object changes, you don't need to get the request. That object is already there because it came to you on a watch request. And then Kubernetes actually periodically resyncs the objects too. Like when you create, let's say, an Ingress controller, that might go out of date because you might go to your cloud provider and fat finger something and do ClickOps. And then an hour later, your controller might actually undo that change because what if we missed something? What if the controller was doing something, the message got lost on the watch request? And so that's why controllers actually do both level triggered and edge triggered reconciliation, right? We kind of look at the grand state of the world as well as the triggered state, which is, oh, just something just changed, right? So you kind of look at both of those things. And your handler, your controller, doesn't really need to distinguish between those things. All you care is like, did an object just got created? Did it get updated? You know, all its resources are reconciled, and did it just get deleted? That's kind of all you care about. So now let's talk about what makes a controller production ready, right? Number one, you gotta tolerate faults. The machine can fail, your controller probably should still continue to work. And number two, as the task load increases, like let's say you're running jobs and you now want to run 10,000 jobs. Does it actually scale to 10,000 jobs on a single cluster? I think that's a very valid question. So the fault tolerance is rather easy, right? You run more replicas of it, and then you kind of ensure one replica is chosen as the leader. That kind of does all the work, you know. And the others are still watching. The others are still kind of, you know, keeping an eye on. So this is an active setup in this case. And as soon as the leader dies, the others kind of perform another leader election, and they take over. And so this is kind of how a lot of the Kubernetes open source controllers out there work, right? If you look at Kube Controller Manager, Kube Scheduler, if you look at the Cert Manager, like all these provide some form of leader election mechanism. And further, if you actually go and develop your own controllers, like using Controller Runtime or Kube Builder, you'll see that there's an option to make your controller highly available by adding leader election using like 2 lines of code. So that's out there. But is there actually a problem with that? So we'll be discussing that shortly. In this case, Kubernetes provides that leader election mechanism through a lease API, right? So that yellow object that you'll see throughout this slide, that is a lease object that basically says leader equals replica 2. Okay, so that sounds great. But how do I do that leader election? Do I use Paxos? Do I use Raft? You don't actually care because Kubernetes under the covers, the API is basically corresponding to one-to-one etcd calls. And etcd itself is a linearizable database, which, you know, in on itself, you can treat it as a black box. So once you write some data into the lease, it will be there, and that will be the final value in the sense that only one write will win among the others, and others will be rejected. So that's kind of how Kubernetes does leader election. And the lease API kind of basically exists for the sole purpose of doing leader elections. So the interesting fields in here is that you can have a holder field, which basically says who's holding this lock right now. And so that's a distributed lock. If you ever like read for example, the Chubby paper from Google, this is kind of what it provides. It's a lock service, right? And the lease duration kind of tells me how long is this lock valid for? Is it 10 seconds, 20 seconds, 60 seconds? How long is that, right? And then I have a renewal time at the end. So now, if the renewal time has passed, I kind of know that, like, you know, basically, last time I renewed plus the duration seconds, if nobody has renewed that lock since then, that lock is up for grabs. You can go and grab it, basically. So there's that. So now, you might wonder, do I need to actually scale my controllers? Like, right, and not everyone needs to scale their controllers. You can like figure out all sorts of ways, but I'll give some examples from real world experience that I might have gained at another company, and I think other companies, I'm sure there are some outbound employees here. Is there anybody working at outbound actually? There's one. Well, that's cool. Okay, I'm glad to hear. So I think there are other companies out there kind of dealing with this problem too. So you know, normally Kubernetes says we support 5,000 nodes, but GK says we support 25,000 nodes. So if I'm doing the math, like, what if I ran 10 pods on each node? That's a lot of pods actually. Like, does my Kube scheduler, you know, is it going to be able to handle that load, right? So that's a very valid question. And if you read the release notes of Kubernetes 126, there was a little note in there. I don't know if a lot of people have realized. Like, basically says if you use Kubernetes job object in a particular way, it supports 100,000 pods. Interesting. So you mean it wasn't supporting that before, right? So that wasn't very scalable, it turns out. And there are a lot of like interesting experimental state-of-the-art projects out there that kind of takes the ideas of Kubernetes API and, you know, try to extract that from Kubernetes and, you know, provide a standalone Kube API server solution. Like, imagine your DigitalOcean, and every time your customers create a VM, create a custom resource on Kubernetes or KCP that is called a VM, and you kind of write your own controls to reconcile that. What if you were DigitalOcean? What if you had like 500,000 VMs out there? Would your controller scale? So I think that's why I think this is a pretty interesting use case. And as you write your own CRDs, your own controllers, you can write objects that are 5 kilobytes, 10 kilobytes long, and you'll soon realize that there are some scalability limits of Kubernetes as well as the controller machinery out there. So now first, let's talk about the throughput. If it takes t time to reconcile n objects, how long does it take to actually reconcile 10,000 times of that? Like, do you think it's 1,000 then? Like, what sort of parallelization do we allow here? What are the limits of a machine? Is the API server throttling us? Is the API server capable of handling that much load? So those are all valid questions. And by using active setup, you're setting only one leader to do work, and all the others are just sitting there watching the world, unfold, and they're kind of keeping track of things, but they're not making any write requests because they're not the leader. So you're kind of creating a bottleneck in your system, right? It's not a single point of failure, but it is a throttling point. So the same goes with memory, actually. This is a real problem that we encountered. We said, our controllers would need 4 gigabytes of memory. Who gives realistically 4 gigabytes of memory to their controllers? Nobody does that. We did that, and we actually ran out of memory. Well, it turns out you go to a very big GK cluster that has a lot of nodes and a lot of pods on them, and each pod takes like 3 kilobytes to represent in the memory, and like every time a full reconciliation, I think you just quickly run out of memory. That the controllers are not very efficient. Ghost structs are not necessary. Go is not doing the best memory management always. But the essence of it is that why would we need gigabytes of memory? That is, I think, the core of the question here. And so every time you run a controller, each controller maintains a local cache of the objects that it was watching, so that it can understand what just got deleted, what just got added, what was the update, so it can tell the difference between those two things, right? And as you do more of these periodic things, you kind of like take the entire state of the world, you have a memory of 100,000 pods in the memory, then you go list them again, congrats, you just have 200,000 pods in the memory. So those sort of stuff happens quite a lot actually if you try to use Kubernetes in a production setting. So today I'm not going to present my own ideas. I'm actually going to take you through a paper that I read recently. This is not very well publicized. I just did Google search and actually came to someone's master thesis that is still kind of work in progress actually. This is a person from Germany who's working at, I think, the Gartner project, if you heard of it. The thesis is called Towards Horizontal Scalable Kubernetes Controllers. So we'll be talking about this master's thesis quite a bit, but if you want to go read that, it's about 50 pages, only kind of like 10, 15 pages are the interesting, relevant part, the rest is kind of an intro. So yeah, what do we need then? What requirements do we have from this sort of scalable infrastructure? First of all, we want to still write controllers, right? We don't want to write something that doesn't look like Kubernetes anymore. And the other thing is we want to be able to add more replicas, and the replicas will come and go based on the need probably. And now we kind of want to prevent concurrent handling of an object, just like we were doing with the active replication with leader election, right? So at a high level, the master's thesis goes into this architecture, which is like, why don't we just create a charter that gets all the objects from the Kubernetes API, it knows which controllers are out there, like let's say A, B, C, D, and it just puts a label. And so it exploits this idea of the labels, because when you create a watch from Kubernetes API, you can say, give me all the, like, I'm only interested in the pods that have this label, right? So now you're in this territory, well, you'll get, instead of 100,000, maybe you'll get 10,000 or only 1,000 objects in the watch queue, and you'll be maintaining only that many objects in your memory. But this is still a problem. Like now the shardr is the single point of failure. This is still a bottleneck. And there are other questions like how does the shardr actually discover the other members of the cluster, like the controllers that come and go, and when a new controller replica comes up, let's say you have 5 replicas and each of them are handling like 20,000 pods, you just added 5 more, do they continue to still handle those 20,000 or do they like kind of redistribute the load, right? So those are like still very much interesting questions. And if you're interested in, if you did anything with databases out there, you probably heard about like partitioning. The thesis recommends that we can essentially use something like consistent hashing. If you've never heard of consistent hashing, this is, you can imagine that we have replicas ABC. We kind of just create some phantom nodes out of them, like let's say A1, B1, C1, A2, B2, C2, and we just kind of hash their names and put them on a hash ring, and every time we get a object, let's say we get a pod object, we kind of hash the entire name and namespace and kind and whatnot, and we find the location that which controller is responsible for this object in the ring, and we just kind of assign it to that object. In this case, you can imagine we just find that red dot on the ring, and then we kind of just reassign it to the right of that red dot. And this is done by actually just going and adding a shard label on the object. That's fairly straightforward. So now we're thinking about how to scale the shardr, because the shardr was a single point of failure, right? So the paper says, why don't we just run more of the shardware as well, right? We can just go watch all the pods, but only the active pod will keep track of the objects, and it will only keep track of the metadata portion. Like, when you create a Kubernetes object, there's the name, namespace, like creation, timestamp, whatnot. What if I only kept that portion and kind of discarded the rest from the memory? Because I don't need to know a pod's spec or a stateful set's history and whatnot to be able to label that object, right? So that's kind of what happens here. It basically says that I'm only going to keep track of all the objects, but I'll only keep track of the metadata portion, which you might argue is, again, not fully scalable, but it actually it can go a great length. I mean, you can probably scale to millions of objects fairly easily by deleting non-metadata fields from there. And multiple sharders among themselves, they still perform a leader election using a lease. So that is fairly straightforward as well. And all the sharder does is that it just labels the pods. That's its job. It labels the objects that the controller is responsible for. So now let's talk a little bit about membership discovery. Let's say you wrote a controller, you're running 5 replicas, tomorrow you're running 10 replicas, you go back to 7. How do you discover these things? This is fairly easy as well. We're basically creating a lease object with the replica's name. And every time that controller replica is alive, it's renewing the lock that has the same name as the replica. Right? And then after a while, you realize if a replica just disappeared, they will stop renewing their lock. And at that point, we can say that the replica is dead. And we should probably reassign the objects on that replica, right? So in this case, the sharder actually waits. Let's say if your timeout is 10 seconds, it actually waits 20 seconds just in case we don't get a zombie situation where the controller comes back or there's a little time skew. The idea is actually from the chubby paper. So now let's talk a little bit about the rebalancing act. So the rebalancing, again, if you add more nodes, let's say in this case I added that green circle to the hash ring. What I need to do is look at that red dot, which was previously assigned to the B node, and I need to reassign that to the green node, in this case that is D. And now I have to kind of find a way to take that object out of B and give it to D, right? I'm changing the responsibility in this case. And this is implemented using a drain label. And the procedure is executed as follows. You just add a drain label, the sharder adds a drain label, and now we realize that that drain label comes to the controller, and the controller realizes, holy crap, I'm not supposed to work on this object, and it stops working on that object, and it removes the shard label from that object so that it looks like the object is not assigned to anyone, and then sharder realizes that I'm going to assign this to somebody, and then goes through the hash ring and does the assignment, and the object ends up in the right place. All this is Kubernetes watches and stuff, nothing interesting. It's just, regular distributed system stuff. So this is an eye chart. I don't expect you to see it from probably, beyond midway through the room. But if you go to the paper, you're gonna see a more complicated, I would argue, that version of what I just explained. In this case, the author actually decides to co-locate the sharder controller and the logic, the part that does the business logic in the same process. So they kind of scale together. And the main reason for that is that this author actually wants to use the controller machinery. They want to use the kube builder, they want to use the controller runtime, they want to actually use all the open source stuff. So when you're in your controller, when you say, I'm interested in the pod object, I'm interested in the stateful set object, I want to watch those things, Sharder knows exactly what to watch in that case. So they're running in the same process. So obviously it comes with advantages and disadvantages. So in this case, the author actually does not find a noticeable CPU gain. The sharder just ends up consuming the same amount of CPU. My theory is that I think they're still ending up deserializing thousands of Kubernetes objects that from Proto to JSON and probably into Ghost struct, so that they're still doing a lot of work in the sharder. So that does not go away magically. And then similarly for the memory, they only find that the active sharder replica uses only 10% less memory, and the others significantly use less memory because the other controller replicas get 1/n objects, right? If you have 5 controllers, you get 1/5 of the objects that you were getting before. So there's definitely some memory gains on other ones, but not the main one. So I think my theory here is that the informer caches that I think running under the covers are still kind of caching the entire object instead of just the metadata. That is TBD, I'm still yet to work on that. So now, the author's thesis kind of ends there. I'm coming with my own ideas. What if we had different ways of publishing messages to the controllers, right? What if we had some sort of pub subtopic, some messaging channel that says, okay, I have multiple, so you can imagine the blue boxes as the dispatchers. They kind of watch the Kubernetes API. They only care about the 1/n objects potentially, right? They can say that any client that connects to me, I'll just give it some objects to be responsible for. So this is not going to be very how to say, like, defensive against the multiple writes happening potentially at the same time. You're not gonna have exactly once delivery guarantees. You're not gonna have order delivery guarantees. You're gonna miss some updates, but again, that's kind of how controllers work. So I think there are more interesting ideas there once you kind of go outside what clients go in Kubernetes ecosystem provides you. If you go outside controller runtime, kube builder, I think you have more options here that are potentially more scalable. So yeah, that's kind of all I had. If you want to read the entire thesis, there is a PDF file in the thesis controller sharding repo. If you search Kubernetes controller sharding, you should be able to find it, and there is code. That's all. Thank you. Hopefully that was fun. Questions? Yeah.
I'm kind of new to Kubernetes, and I've heard the term operator as well. How does that compare with controller?
Operator basically is a controller that knows how to manage something a little bit more sophisticated. There are I don't think there's actually a difference. I think it's a marketing term. If that makes sense.
That's kind of how
Like, let's say you develop a MySQL operator that knows how to run MySQL on a bunch of machines. It just knows the operational details of how to take care of nodes and how to do backups and stuff like that. That is an operator.
Thanks.
Any other questions? All right, so okay. So I brought some t-shirts. There's only one size each, so sorry about that. I think there's no smalls or anything.
I stole it.
There are a lot of GitHub stickers here. If you're interested, feel free to grab them as well. They're pretty fun. Yeah, there's one question.
Do you have any more Twitter t-shirts?
Unfortunately, no.
No.
I'm keeping them as memorabilia.
Right.
And yeah, Jerome, I asked Jerome Pizzoni that exact question, and he said a controller is a control loop that manages stuff, and an operator is typically a controller plus a CRD.
I think a lot of controllers have a CRD. I mean, it depends. Yeah. That's an interesting description. Yeah. Yeah, go ahead, please.
I'm curious that your thoughts on rather than developing a sharding strategy on these things. How does it compare? Actually, you have federation but multiple cluster, and you control the size of each cluster. So you can kind of limit the number of pods for the controller handle.
Yeah, I think like the federation probably is a separate discussion that warrants its own. But if you have a way to actually split work, let's say you run 100,000 pods and they end up in 10 different clusters, then potentially you can actually run a mini controller in each of these clusters, or you can run the cluster at the parent federation control plane, right? Again, pluses, minuses there. You can only do, you're operating within the confines of what you can do, right? Like, so essentially at the end of the day, there's a Kubernetes API, you're working against that. Does that scale? What are the limits of your controller? Yeah, I think it comes down to that.
One more question.
So you kind of touched on the topic of leader election as an option, but we didn't really talk about some of the other common options other than leader election, such as like, can you touch on that maybe?
Yeah, we didn't talk a lot about the other options. Potentially, are you referring to the, like, let's say we run multiple controllers and we choose a leader, is that what you're
Yeah, so in that case, you have one leader is kind of doing all of the work,
Yeah.
right? And so what if you want to spread that workload out across multiple work pods,
Yeah, essentially that's what the sharding does, right? So by labeling the pods with the number of shards that we have, we kind of assign the workload without needing any coordination through a central mechanism like leader election. So that coordination essentially becomes redundant or obsolete in that case, because the replicas only look at the number, like the labels that they are responsible for, and the labels get adjusted as the replicas come and go. Yeah, was that answered?
Yes,
Okay.
perfect, thank you.
Yeah. So no longer leader election basically in this
Yeah.
model.
Thank you to our
Thanks,
speakers. There's also a bunch of great stickers up here, so stop by, cover your laptops. A couple housekeeping. Next time we will have a microphone and a speaker. So thank you to all in the back for coming but not hearing.